Hello, I'm Henri Lunnikivi. I research embedded AI at Tampere University. I'm here to give a quick intro to our research topic, transpiling Python to Rust for optimized performance. Let's start with Python. In machine learning and scientific computing research, Python is very popular. While Python by default is slow, it is highly optimizable with techniques like pre-compilation and just-in-time compilation. These methods, however, generally leave some performance on the table. The culprit behind most hard-to-optimize problems is control over memory access. Python's runtime memory management strategy works great for many applications, but when it doesn't, it gets hard to work with. Small microcontrollers are particularly affected by limited amount of memory and smart use of caching. Let's look at some of the popular ways to address memory overhead in applications developed with Python. If you're working with machine learning, you may be able to use end-to-end optimization via TensorFlow and TensorFlow Lite. Most Python-based implementations can use various degrees of pre-compilation and just-in-time compilation to achieve almost native-level performance. Some of these approaches are limited in that Python itself cannot know whether a certain block of memory can be shared or if it needs to change. Memory overhead is introduced. Sometimes you can't accept the overhead. For instance, when you're the platform producer for 1 million users, or when you're working on a particularly resource-constrained device, or when you're trying to accelerate these libraries like TensorFlow themselves. In these cases, you might want to go as close to metal as possible, so you switch to a compiled language with low-level control that lets you compile your high-level program into native code. Examples of such languages with low-level control are C and C++, Rust, and assembly. But there's an intuitive problem with zero-overhead languages. Zero-overhead languages tend to also be low-level languages. The best way to assure a computer behaves the way you want it to is to define very clearly, using low-level primitives, what it is that you want the computer to do. The best example of this sort of low-level control is assembly, which lets you define instruction by instruction what you want the processor to do. One step further from that are C and C++ that let you kind of forget about instructions, but instead allow precise memory control. Rust is a level further in that it allows you to stop micromanaging the memory, as long as the compiler can figure out a way to sort it out. Being free of the memory management related code, we thought that the level of abstraction of a language like Rust was so close to Python that we chose to try and transform our program. We found this remarkably easy. So that in principle is what our paper is about. We converted two applications from high-level Python to syntactically equivalent high-level Rust and measured the differences in execution speed and memory use on a few different platforms. We also enabled the program to compile on a mobile platform where we originally could not run the Python version. Here are the results. This use case, motion planning, calculates the three-dimensional path for a robotic arm using an iterative differential calculation. We measured wall clock execution time and peak memory consumption using Valgrind. The three columns are the Python implementation, the Rust implementation dispatched from a Python runtime, and a Rust implementation without a separate runtime. All implementations, both Python and Rust, use data parallelism with Intel MKL to accelerate matrix multiplications over multiple cores. As you can see, the execution time improves almost tenfold, and peak memory consumption is slightly improved. We believe correct optimization of multi-core memory management to be responsible for the speedup. For memory, we believe that the difference between the first two columns is unnecessary overhead eliminated by the compiler, and the 2 megabytes of difference between the other two columns seem to match with the size of the Python interpreter. We also made measurements without Intel MKL acceleration using OpenBLAS. In the OpenBLAS accelerated environment, the speedup is only close to twofold, but memory use improves fourfold. We also measured the implementations on an ARM A9, the CPU of the PYNQ Z1 embedded platform. On the embedded device, execution speed does not significantly change, but the memory consumption is again improved fourfold. Finally, we measured another much smaller benchmark called Black-Scholes. This application calculates a value for a few million of stock options. We pulled a Black-Scholes benchmark implemented with NumPy and Python from the internet. Originally, it took almost 30 seconds to run for 72 million stock options. We then transpiled the syntax and corrected compiler errors. Running this native Rust version took less than 12 seconds and reached peak memory consumption that amounts to a third of what the Python implementation required. In this very small use case, applying a simple syntax conversion and correcting the resulting compile errors made the program almost 3 times as fast and 3 times lighter in memory. Our use cases are limited, but the method seems to work. Transpiled implementations are generally faster, use less memory, and produce a smaller peak memory consumption. The method integrates well into a Python ecosystem. It's possible to pick a small workload, optimize it, and call it from Python. Alternatively, for a sufficiently small application, it's possible to fully transpile, to remove the Python runtime. Our very limited use case seems to suggest that transpiling small workloads of high-level Python to high-level Rust seems to be an easy and effective way of reducing memory consumption and making the application faster, without losing readability of the high-level code. Thank you. If you have any questions, feel free to contact me using the address on screen.